Hi, it's Dr. Harris, and we're back uh, fresh off our video for the sampling distribution demonstration. I hope you've watched that somewhat recently, and we're here now to begin seeing how we can use that to say something about confidence intervals. What we've got here right now is the table that appeared at the end of the demonstration slideshow. Uh, and what we noticed is that we were looking at trying to approximate the sampling distribution of a sample proportion. That is, we took a large number, I think 10,000 samples of various sizes, and we computed sample proportions from a population that had proportion zero point 0.7. And what we discovered is that for various sample sizes, I looked at 4 different sample sizes, the distributions all looked bell-shaped, normal, and they were all centered right around the population proportion 0.7. But what we did notice is that based on some eyeball estimations, it looked like the standard deviation was dropping by a fair amount as the sample size increased. And so I've got that summarized here on the next slide. Bell-shaped curves for the distribution of p hat, centered at the population proportion, as we noted in the exploration that we did, that was 0.7. And in terms of the spread, as we just pointed out, as sample size increases, standard deviation seems to go down. But that phrase, standard deviation of the sampling distribution, is a bit of a mouthful. We're going to have a different term for that. We're going to call it the standard error of the distribution. And as we go through chapters 5, 6, and 7, we'll see a variety of formulas for standard error depending on the statistic that we're interested in. Here, in the case where we're talking about a single sample proportion, we're going to use the notation SE sub p hat. And we did notice that the standard deviation seems to be going down. The standard error seems to be decreasing as sample size increases. It'd be nice if there were a formula for it. And we are proposing here that formula for the standard error is the square root of the population proportion times 1 minus the population proportion divided by the square root of the sample size. So p times 1 minus p over n, we compute that fraction, we take the square root of it, and that's our expression for the standard error. Now, I'm sort of asking you to take that on faith, but we will do a couple of calculations to demonstrate that it seems to be a reasonable formula. It is the correct one. But let's compare what we eyeballed with what the formula produces. So when p is 0.7, n is 100, we plug that into the p times 1 minus p over n, square root of all that expression. We get, for sample size 100, 0.046 approximately. That's a little bit less than the 0.05 that I proposed, but it's in the neighborhood. Another one with n equal 400. If I calculate the square root of 0.7 times 1 minus 0.7 over 400, I get about 0.023, which again is in the neighborhood of the estimate that we had, which was 0.025. My estimates were, in both cases, were a little bit on the high side, but because they're so close, it seems like we've got some evidence that maybe this formula has something going for it. And so the square root of p times 1 minus p over n is the formula we're going to use for standard error in the case of a single proportion. That's an important proviso. We're going to have different standard error formulas in different cases. But we're going to see soon that while this is correct, we're not going to be able to use it. So let's hold on to that thought for a minute while we talk about introduce one of the primary results in elementary statistics, the central limit theorem, which basically says, in the case of a single proportion, that when we have enough samples, if our sample size is big enough, and the observations can be considered to be independent of each other, then the distribution of p hat will in fact be normal, with mean centered at the population proportion and standard error equal to the expression that we encountered earlier, square root of p times 1 minus p over n. A good question to ask at this stage is, what does it mean for the sample to be large enough? And If we have a random sample that's big enough, we're going to be able to apply the central limit theorem in a modified form. But that condition that we need to check to see if it's big enough is we take the sample size and we multiply it by the population proportion. If we can think about it, if we took a single observation from the population, the probability that we'd have a success is p. And so n times p is going to be the expected number of successes when we draw n individuals from the population. And so if we expect at least 10 successes, and then we look at 1 minus p, that's going to be essentially the probability of getting a failure in a single draw from the population. So n times 1 minus p is going to be the number of expected failures. And so if that is also 10 or bigger, then we're going to say that things are good enough. So we need to have at least 10 expected successes and 10 expected failures in order to proceed. Just a brief rationale for that. If the population proportion p is pretty close to 0 or pretty close to 1, it's going to turn out that the distribution of p hat is a little bit skewed, and we're going to need a pretty big sample size to overcome some of that skew. So in order to conclude that we've got roughly a bell-shaped distribution, we're going to need to have either a p-value, a value of p that's pretty close to the center with a big enough sample. But we need to check to see, are there at least 10 successes and 10 failures expected? So it's going to be what we call the success failure condition. And it's something that we're going to want to check each time before we can proceed. So here's an example. We're going to calculate a standard error. Suppose that it turns out that 18% of all US drivers know how to operate a manual transmission. If you took a random sample of 500 adults, would the success failure condition be met? And if that is the case, what would we say the mean and standard error of the distribution of p hat are? Well, p is 0.18. If the proportion of all adults that can operate a manual transmission is 0.18, then p is 0.18, n is 500. So we can calculate n times p, we get 90, definitely bigger than 10. And 1 minus 0.18 is 0.82. 500 times 0.82 is 410, again, well over 10. So the success failure condition is met. And so the center of the distribution will be the population proportion, 0.18. So the mean is 0.18, and the standard error then would be the square root of 0.18 times 1 minus 0.18 over 500, which turns out to be about 0.0172. So success failure condition is checked. If we have success, then we can calculate the mean and standard error of the distribution of p hat. But there's a small problem with this. We don't know ordinarily, as we've said, the value of parameters. We don't know p. So the standard error formula uses p, and so I can't use it to calculate the exact value of the standard error if I don't know what p is. Our solution, as I've noted here, is assuming the success condition failure is met and we've got independent observations, then we're going to replace p in that formula for standard error with p hat. And so our standard error formula that we're going to use, and it's an approximation, is going to be the square root of p hat times 1 minus p hat over n. So we can go back and look at a case where we calculate this approximate standard error. So using the manual transmission example, suppose that we really didn't know that the figure was 18%, and we took a sample of size 500, and it turned out that 0.192 was the sample proportion. 19.2% of the adults said that they could use a manual transmission. So since we would have to apply the success failure condition to our sample proportion p hat, and so we'll multiply n times p hat. That will give us 96, still bigger than or equal to 10. N times 1 minus 0.192 is going to be 404, also well bigger than greater than or equal to 10. So the success failure condition can be checked with a sample proportion as well as a population proportion. In fact, in reality, we're going to have to check it using the sample proportion. So once we have that condition met, we can approximate our standard error by using p hat, the square root of 0.192 times 1 minus 0.192 over 500 is very close in value. It's 0.0176, but it's a little bit different. But this is the figure that we would wind up using in actual statistical work. So the point I'm trying to make here, I guess, is that the approximate standard error is very close in value to the actual standard error ordinarily, because we expect the sample proportion to be fairly close to the population proportion. So now let's go on and talk about confidence intervals. Now that we've got some base knowledge about the distribution of p hat, a little bit about formulas for standard error for a sampling distribution. So now let's think about what do we mean by confidence interval. And we're going to start by doing a little refinement of our 6895 rule that we encountered back when we were talking about normal random variables. So what we said before was that approximately 95% of all observations from a normal distribution are within 2 standard deviations of the mean. In reality, it's not quite 2, it's 1.96. And so that italicized statement there, in a normal distribution, exactly 95% of all observations are within 1.96 standard deviations of the mean. So we can consider this sort of a modified 6895 rule. And you can see an illustration of this in your textbook on page 193. So I invite you to stop and take a look at that. So here's the deal with coming up with trying to understand what a confidence interval is all about. It's going to require us to change our perspective, change our point of view. So the central limit theorem says that 95% of the time, the sample proportion will be within 1.96 standard errors of the population proportion, because it's going to be approximately normally distributed. But since we don't know the population proportion, this isn't a useful way to state this. And so what we need to do is we need to turn things around and look at it from the other side, another point of view. So instead of saying 95% of the time the sample proportion should be within 1.96 standard errors of the population proportion, we can actually turn it around and say that 95% of the time we expect the population proportion to be within 1.96 standard errors of any given sample proportion. Okay, so we'll say that. So before we go in and try to repeat that, let me try to give you another example here on how this is what I'm trying to say here. Suppose that I'm person A in this scenario, and person B is one of you in the classroom. If you and I are standing within 10 feet of each other, then one way to say this is if you look at it from your perspective, you could say that I'm standing within 10 feet of you. But from my perspective, you're standing within 10 feet of me. And so that's the exchange of perspective that we're trying to get at here. So let me go back and look at these two statements again. The central limit theorem says that p hat should be within 1.96 standard errors of p 95% of the time. But what we want to turn around and say is that p will be within 1.96 standard errors of any given value of p hat 95% of the time. And that's the foundation for a confidence interval. Okay, so we don't know p. We draw a random sample. We know the size of that random sample, and we can compute p hat, the sample proportion, and the approximate standard error. Square root of p hat times 1 minus p hat divided by n. So what we're able to do then is if we know that 95% of the time p is going to be within 1.96 standard errors of p hat, what I can do is I can subtract 1.96 standard errors from p hat, and I can add 1.96 standard errors to p hat. And what I'll get is I'll get an interval, a range of values that 95% of the time we expect p to live on it. So what I mean by that is 95% of all possible intervals that we could compute this way for all the different values of p hat, 95% of them would contain the population proportion. So the interval p hat minus 1.96 times the standard error to p hat plus 1.96 times the standard error is what we're going to call a 95% confidence interval for p. We're 95% confident that the interval we've just constructed will contain the population proportion p. So this word confidence is a new thing for us. Let's talk about this a little bit more. It feels like maybe we should say there's a 95% chance or we have a 95% probability. That's not the case. Let's try to understand why that is. So let's try to understand the difference between probability and confidence. I've got a couple of examples here. So if you were about to flip a coin, you know that if it's a fair coin, then there's a 50-50 chance that it comes up heads or tails. So we'll say the probability of getting a head in a single flip of a coin is 0.5. So we have a probability before we flip the coin. But if I take the coin, flip it, and stick it on my arm covered up, the coin is either head or tail at this point. It's not going to change. So it's heads or it's tails, but there's no probability, there's no chance left to it. So before the coin was flipped, we had a 50% probability of it being head, but now, without looking at it, we're 50% confident that it shows heads. So confidence is what happens after the random process has been run. So if we're about to take a simple random sample from a population, the 6895 rule, our modified version says, before we draw the sample, there's a 95% chance that p hat will be within 1.96 standard errors of p. But after we draw the sample, if I form the interval, it either does or does not contain p. And so there's no probability attached to this anymore. There's only confidence in the method. So again, before the sample was drawn, there was a 95% probability that for any given p hat, that the p would be within 1.96 standard errors of p. But after the sample's drawn, and we've calculated p hat, p is either within 1.96 standard errors or not. There's no probability anymore, but we're 95% confident the method that we're using will contain p. The interval we construct will contain p. So it's a method that works 95% of the time. So let's work some examples. We're going to be working with this automatic transmission, this manual transmission example some more. We take a random sample of size 500. 96 of them say they can drive a manual transmission car. Let's construct a 95% confidence interval for P. P stands for the proportion of U.S. adults who can drive such a vehicle. P hat, well, to calculate sample proportion, it's the number of successes over the number of trials. We have 96 successes over 500 trials. That's 0.192. This is the value of P hat that we explored a few slides ago. The success-failure condition was met, and the value of the standard error in this case was 0.0176. So if you need to go back a few slides and review, please go ahead and do so. But those are the numbers. That's what we came up with back then. So to form our confidence interval, we're going to subtract 1.96 times the standard error. It's going to give us about 0.158. And we're going to add 1.6 times the standard error to our sample proportion, and we'll get 0.226. And so we're 95% confident that the population proportion of U.S. adults that can drive a manual transmission is between about 16% and about 22.5%. So we're 95% confident that the true proportion is going to be between 15.8% and 22.6% of U.S. adults. So again, the steps here: find the value of P hat, check the success-failure condition, find the value of the standard error, and for a 95% confidence interval, we're going to multiply the standard error by 1.96, and then subtract it from the standard error, from the sample proportion, and add it to the sample proportion. Okay, so again, just to review what we mean by 95% confident, what it means is that if we did this over and over and over again, we conducted samples of the same size from the population, then we're using a method that 95% of the time generates an interval that will contain the population proportion, which of course means that 5% of the time it won't work. So as you see here in parentheses, the method that we're using is designed to fail 5% of the time. But we're using a method that works 95% of the time. That means that's why we say we have 95% confidence in any single interval that we construct containing the population proportion P. Of course, we don't in real life take many samples. We just do one. So we're just going to construct one interval. We don't know for sure whether or not the population proportion lives in the interval, but we are 95% confident that the interval does contain the proportion. So let's observe that we don't always deal with 95% confidence. Sometimes we want a method that works only 90% of the time, and sometimes we want to use a method that might work 99% of the time. So question we want to ask, and I'd like you to think about before you move to the next slide, and maybe before you advance this video anymore, is if I wanted to be just 90% confident of making sure that the population proportion was in the interval, would my interval be narrower than the 95% confidence interval, or wider than the 95% confidence interval? And then I want to ask the same question about a 99% confident. If I wanted to be 99% confident in my method, would I take a wider interval or a narrow interval? So maybe stop the video, think about that for a minute, see if you can come up with an answer, and then we're going to move on to the next slide. So lower confidence means that hopefully you've got a sense that lower confidence means that we can take a narrower interval. If we want to be less sure, less confident in my method, if I want to have it work less often, I will take a smaller range of numbers. Whereas if I want to be more sure of capturing the population proportion a greater percentage of the time, then I would take a wider range of numbers. If I want to be more confident in my method, a phrase I've used in classes in the past is, I want to cast a wider net. So to be more sure of capturing the population proportion, I need to cast a wider net. So a 90% confidence interval will be narrower than 95%, and a 99% confidence interval will be wider than a 95% confidence interval. So let's talk about a general formula for the confidence interval for a single proportion. So the thing that's different here is the introduction of this z star. So my interval is going to be p hat minus z star times the standard error, square root of p hat times 1 minus p hat over n, to p hat plus z star times the square root of p hat times 1 minus p hat over n, where z star is going to be a value that depends on the level of confidence. We've talked about 3 different levels of confidence so far, 90, 95, and 99%. And you can imagine then that we're going to have a different value of z star for each of those. So what do I mean by z star? It represents the number of standard errors that I'm going to use, subtract from, and add to my sample proportion to get the confidence interval. And so it's the number of standard errors I must use to capture a particular percentage of the area underneath a normal curve. We know from what we've discussed earlier that when we're talking about 95%, 1.96 standard errors, either direction will capture the middle 95%. For 90%, we'll use a smaller multiplier. We'll get a narrower interval that way. 1.65 is the value for z star that's used. That's what captures the middle 90% underneath the normal curve. For 99%, z star is going to be 2.58. One more thing I want to talk about before we do another example. That's the expression margin of error. We'll say more about this in class and maybe when we get to chapter 6 as well. But this expression z star times the square root of p hat times 1 minus p hat over n is our expression for margin of error when we're talking about finding a confidence interval for a single population proportion. We'll have different expressions for margin of error for different statistics. So, and that it's all tied up in the formula for standard error. Here, this is z star times standard error, and that's going to be we're going to have similar expressions for margin of error for other statistics. So let's compute a 99% confidence interval for our manual transmission example. Our sample proportion was 0.192. Our standard error was 0.0176. Our new value of z star for 99% confidence interval is 2.58. And so when we do the calculation, we multiply 0.0176 by 2.58. We subtract it from 0.192. We add it to 0.192. We get 0.147 and 0.237 respectively. So we would say that we're 99% confident that the proportion of US adults who can drive a manual transmission car is somewhere on the interval between 0.147 and 0.237. Let's talk about margin of error in both of these cases. The margin of error for the 95% confidence interval was 0.034. Now, how did I get this? Let's go back. Our confidence interval, we're back quite a few slides. Our confidence interval was between 0.158 and 0.226. The margin of error is this number right here, 1.96 times 0.0176. And if you multiply that out, you'll get about 0.034. And so that's our margin of error. And so we would say that 3.4 percentage points is the margin of error in the 95% confidence interval in this case. Whereas 2.58 times 0.0176 is 0.045. So our margin of error for the 99% confidence interval is about 4.5%. Hopefully we expected this to happen. When we increase the confidence level, we expect margin of error to go up because z star has gotten bigger. So our margin of error is going to be getting bigger as well. So just a few warnings about interpreting confidence intervals for the moment. We'll be looking at more of this in coming slideshows and chapters. There are several incorrect ways to interpret a confidence interval. Here are a few. It's not correct to say that there's a 95% probability that the population proportion will live on the confidence interval. Remember, probability is something that we use before the sample is drawn and before p-hat is calculated. Once the sample is drawn, we now talk about confidence, not probability. It's also not correct to say that 95% of all the values of the sample proportion live inside the interval. That's the point of view standpoint that we can't use here. What we want to say is that 95% of the time, the sample proportion will live within 1.96 standard errors of the population proportion, but not 95% of all sample proportion values will live inside the interval. They would live in an interval 1.96 standard errors around the unknown population proportion. And it's also incorrect to say that 95% of all observations live inside the interval. If the sample proportion values don't live inside the interval, individual observations aren't going to live inside the interval either. Remember, we're using a distribution for sample proportions, not individual observations. And finally, here is a practice problem that I'd like you to work. We'll talk about this when we get together in class. I want you to practice it, try it, and then maybe I can give you the answer in class, and we can talk about it, see if you need some help with it. Suppose that you wanted to estimate the proportion of college students who average less than 6 hours of sleep per night. So you go to 800 randomly selected college students, you ask them, do you average less than 6 hours of sleep per night? They will answer yes or no. That's categorical data. We're talking about calculating a sample proportion for those 800 randomly selected students. First, I want you to verify that the success-failure condition holds, and then compute and interpret a 90% confidence interval for the population proportion of college students who get less than 6 hours of sleep per night. So something for you to work on, and we will talk about that. Check your work when we get to class sometime.